Hello everyone, I'm Wei Shen. First, I would like to thank the workshop organizer who gave me the opportunity to share our recent work in this workshop. It's a little bit unfortunate that I cannot attend this workshop in person due to the outbreak of COVID-19 in Shanghai last month. But I will try my best to give a good presentation online. The topic of my talk is detecting gaze targets from images captured in the wild. Gaze behavior is a critically important aspect of human social behavior, visual navigation, and interaction with the 3D environment. Gaze target detection is also known as gaze following. Its goal is to infer where each person in a scene is looking. So we know that this can be achieved by wearing eye trackers. However, wearable eye trackers are burdensome to participants and is not sufficient to support the large-scale collection of naturalistic gaze data. So this is why we would like to detect gaze targets in images. So existing methods almost adopt this kind of dual stream framework. So first, each human hand location is given. This can be achieved by either annotation or head detector. Then a thin branch takes the whole image as input to detect the stringency regions in the image. For example, we can detect this kind of stringency regions here, 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 and here, right? So this stringency region at the candidate gaze at the candidate region of gaze targets, because we know that a human when a human is looking, what a human is looking at is usually a stringency object, right? And meanwhile, head branch take the head image crop, for example, this crop, to do gaze estimation. So this module will output a field of view. The field of view is a region with a cone-like shape. You see like this. So the sunlight of this cone is the predicted sunlight given by the gaze estimation. Then the intersection of the stringency region. And the intersection of the stringency region and the field of view is the candidate region of the gaze targets. And we can do this one human by one human. Then we detect gaze targets of all humans in this thing. So you see, this framework is intuitive, and we can find that the key steps in this framework are stringency detection and gaze estimation. However, existing method many use 2D gaze estimation. The lack of thin depth understanding lead to detection failures. Here we see the yellow line is the ground truth sunlight, and the red line is the predicted one. The reason for failure is the gaze estimator is unable to know whether the human is looking forward, backward, or sideward. Okay, so the failures are caused by the lack of thin depth understanding. In addition, since the field of view of a 2D image is limited, there is an out-of-frame issue when detecting gaze targets in 2D images. And this issue happens frequently. For example, in the video attention target dataset, 1/3 gaze targets are out of frame. So which means the human is watching out, right? So the gaze target is not in this image. Third, current framework requires head detection as a preliminary step, and usually assume that the head crops are given, which breaks the principle of automatic scene understanding. Although one can perform head detection first, the errors in head detection will be accumulated subsequently. So to address these three issues. We propose three methods, respectively. So the first one is to involve depth attention in gaze target detection. This work was accepted to CVPR 2021. The title is Dual Attention Guided Gaze Target Detection in the Wild. Now I introduce the first work. This is the pipeline of this work. We propose a dual attention guided gaze target detection framework. First, given the helicrop here, you see, helicrop here, we do 3D gaze estimation rather than 2D, and will also involve eye detection here to calibrate the gaze estimation results. The result of 3D gaze estimation provides the important depth information, GZ, here, GZ, okay, of the gaze target. So you can understand that this information actually indicates whether the human is looking forward, backward, or sideward. Then we use a depth estimation network, okay, to estimate the depth map of the whole image. And combining the depth map and the depth information outputted from the 3D gaze estimator, GZ, we can narrow down the search space across the depths to form the depth attention. So now we have the depth attention. Then we have the use a field of view generator to generate the field of view attention. This is a typical one. Use the same method as the previous, same strategy as the previous method. So you see, it started at the head location, and the center line is the side line. The shape is is a cone-like shape region. Okay, and then we have the depth attention and the field of view attention. We combine the two together to locate the candidate region for the gaze targets. So this is the dual attention map. We'll combine the this dual attention map and the original input image. Based on them, we use a deep network to do gaze target detection, and also to predict whether this gaze target is out of frame or not. Okay, I think this is also an intuitive framework which involves the depth information to help us to more precisely to locate the region of the gaze targets. Now we see the experiment results. We compare against several state-of-the-art methods on gaze follow and video attention target datasets. We can observe that our methods outperform previous methods significantly, even towards human performance. Here we show some quantitative results, and we see our method can precisely predict gaze target with a large distance in depth. And I will also do some ablation study to show the contribution of each component in our framework. Here we see the most improvements brought by the dual attention module. Right? So which evidence that to combining the depth attention and the field of view attention is very effective for this task. And I also show the visualization for this application study. Take the first one as example. So here this is the given head crop image, and we estimate the depth attention remember that this is the intersection of the depth map and the candidate region given by the depth estimation from the GAZE estimation. We have this candidate region. Okay, and this is the FOV tension. This is cone-like shape region. Okay, and combine the two, we have the dual tension region, which is the candidate region for the GAZE target. And this is the heat map from the given by the dual tension map. And the peak of the heat map is the location of the GAZE target. Okay. And we do more evaluations, including GAZE direction evaluation. So this result shows that our 3D GAZE estimation method outperform previous method. And the evaluation of depth estimation show that with a stronger depth estimator, our method can achieve better results. Okay. Now we introduce the second work, which detect GAZE targets in 360-degree images. The title is looking here and there, GAZE following in 360-degree images. This work was accepted to GAZE 2021. So remember that we claimed that there's an out-of-frame issue in GAZE detection in 2D images because 2D image has a limited field of view. 360-degree image provide an omnidirectional field of view and can alleviate the out-of-frame issue. So we try to do GAZE target detection in 360-degree images. But currently, there's no such dataset. So we collect one, which is a large-scale dataset containing over 10,000 equirectangle images, sampled from 55 videos from YouTube. So it is diverse, content interview, outdoor activity, reality show, this kind of things, including both indoor videos and outdoor videos. The quality of the dataset is high. The resolution of images is 4K, and each GAZE point is annotated by about 4 people for each image. Here we show some statistics of the GAZE data in our dataset. We show the histogram of the location of GAZE targets and human subjects, as well as GAZE direction. So this statistics show that the diversity of the GAZE data in our dataset. However, detecting GAZE targets in 360-degree images raises a new issue. Previous method all used FOV attention. Z has the assumption that a GAZE target is in the 2D GAZE sightline. This is true in 2D, right? For example, for this example, we can see that this is true, right? This is the sightline, this is the GAZE target. However, this is no longer true in 360-degree images, especially for long-range GAZE behavior. Due to distortion brought by severe to plane projection. You see, for this long-range GAZE behavior, this assumption is no longer true. The distortion is severe when the human and the GAZE target are far away, while the distortion can be ignored within a local region. So we can still make this assumption for short-range GAZE behavior, for example, this one. This actually motivated us to propose this dual-path framework to handle both long-range GAZE behavior and the short-range GAZE behavior separately. So in our framework, we first estimate 3D GAZE direction from the given head crop image. So here, this is the 3D gaze direction estimated from this head crop image. Then the local pathway uses the field view attention, the cone-like shaped region to search the gaze target within a local range of the human. You see, this is a local range. And the distant pathway handles long-range gaze behavior. First, we map the equirectangle image to a sphere by the inverse sphere to plane projection. Then started at the head location. We search along the 3D gaze direction in this sphere space. Okay. And then we locate the interaction of the sideline and the sphere. Here we have the we have the intersection here. Okay, and then we use a Gaussian kernel center at the intersection as the attention map. Okay. The heat map obtained by both the distant pathway and the local pathway are combined together to form the final gaze target heat map. And we will paste this heat map actually computed from local region, right? Local region. So we will paste them back into the whole image to form the final heat map for the gaze target. Okay, so this is our two pathway framework. Okay. So previous methods usually use the L2 distance between the predicted gaze target and the ground truth gaze target to evaluate the evaluation metric. However, in the equirectangle image, the L2 distance is no longer proper, so we define a new evaluation metric, the sphere distance, which is the shortest distance between 2 points on the surface of the sphere. And we also use the area under curve criterion to access a predicted gaze target heat map. Here we show the experimental results. You can see that our method achieved significant improvements over previous 2D gaze following method, which show that in detecting gaze targets in 360-degree images require the 3D information. So the assumption used in the 2D gaze following method is no longer proper here. And we also do some ablation study to show the contribution of each component. Here we see both of the DP is the distant pathway and LP is the local pathway. We show that both of the two have positive contribution to the final result. Here are some quantitative results. Here we show that for long-range gaze behavior, our method can precisely predict the gaze target. But as a method, they fail to do this. Okay, now I will introduce the our third work. End-to-end gaze target detection. The title is End-to-end Human Gaze Target Detection with Transformers. This work was accepted to CVPR 2022. As I just described, existing methods require head detection as a preliminary step, so they are enforced to be two-stage, since they require head location input. They can only predict gaze targets one by one. So this will also introduce natural computational cost if there are a lot of human in the images. Besides, existing methods predict series maps and gaze directional separately. So this method lacks conceptual relational reasoning for interactions between them. So we have question: can we detect all humans as well as their gaze targets end-to-end? Right. So actually, we find that human gaze target detection is very similar to human object interaction detection. Both of them are high-level seeing and stunning tasks. So for human object interaction detection, the recent methods are all based on data-based framework. So I think everyone should familiar. I assume everyone is familiar with DITR. DITR is a transformer-based object detector to detect objects based on transformer. So it includes some object queries in the decoder and use Hungarian algorithm to match the query to each ground truth object. And the framework for human object interaction, short for HOI, HOI detection is very similar to DITR. You see here, it also inputs the image, computes the feature map of the image, and use some HOI queries to decode the location of each HOI prediction. Okay, so in HOI, HOI instance is a tuple of human object interaction label. So we can use this concept for human gaze target detection. We can see that the correspondence between the instance of human gaze target detection and human object interaction detection. So human is human, the object is gaze target, and the interaction is gazing. Okay, so we have an idea that we can actually treat human gaze target detection as a human object interaction detection. So we follow this data-based method. We follow this data-based HOI detection method. We propose HGTTR. Right? We aim to detect all humans at once, as well as their gaze targets by transformer based on image-wide conceptual innovation modeling. Okay, so this is our rough idea. Based on this idea, we need to redefine the problem. So previously, previous methods detect the gaze target of each human one by one. So the formulation is like this. The T is the gaze detection module. So previously, the problem is to maximize this problem. Is to maximize the probability of the gaze target location given the image X and also the head crop image. Okay. XHJ is the J is the index of the human head crop image in the image. Okay. Then in our case, since we do this end-to-end, we no longer need the human hand crops. We do this end-to-end, so our problem becomes to maximize the probability that each human hand and its corresponding gaze target location given the whole image. So you see the mathematical form definition for the previous setting and the current setting, the difference between them. Here is our method, which is very similar to DITR. So given an image, we first compute the features by CM backbone. Then we feed the features into a transformer. As a decoder, we input some HGT queries and match them to ground truth HGTs by Hungarian algorithm. Each HGT instance contains head location and the label to indicate whether it is head, and the label indicate whether it is out of frame, and also the gaze location represented by gaze heat map. So accordingly, our loss function has four terms. L box is the box location loss, including an L2 loss between the predicted head location and the ground truth head location. So this is a typical bounding box regression loss. And GLU is generalized intersecting over union loss, which was widely used in object detection. LH is the classification loss for head label, and LW is the classification loss for out of frame classification. So both of the two can be implemented by the cross-entry loss. LG is the L2 loss for get target heat map regression. So this is implemented by L2 loss. And the final loss function is the weighted sum of all these loss functions. So these are the experiment results. As the results shown in this table, our method outperforms others significantly. Since previous methods all take the annotated head crop images input, while our method just takes the whole image input, we report the result into two different settings. One is the default setting, directly use annotated head crop image input. The other is the real setting, which use the detected head crop images input. So we can observe that either method all suffer from performance degradation and real setting, which evidence that errors in head detection will influence the results of gaze target detection. This phenomenon we also mentioned at the beginning. Right? The errors in the head detection will be accumulated in the subsequent steps. Here we show more results. This will show two advantages brought out by our new framework. Our method is based on a transformer which has a strong ability in modeling long-range context. So we can observe that previous methods suffered from significant performance degradation for long-range gaze behaviors. When the human and the gaze targets are far away, it's harder to detect the interaction between them. So we see the significant performance drop of other methods. But we can see that the performance drop of our method for this long-range gaze behavior is much smaller. In addition, since our method is end-to-end, so with the increase of the number of humans in an image, no actual computational cost is introduced. But for previous methods, their computational costs are increased accordingly. Finally, we show the quantitative result of our method. We can precisely detect gaze targets even there are a crowd of humans. Okay, and last we give the conclusion. So human gaze target detection images is a high-level things understanding task. So it requires some actual priors such as depth simulation to help us to precisely locate the gaze targets. And we think the model to do this task should have the ability to infer the gaze targets in omnidirectional field of view. So this can alleviate the out-of-frame issue. And the model should also has long-range contextual modeling ability, because sometimes the distance between the human and the gaze target is very long. Okay, so this is my talk. Thank you. Thank you for listening.